Alright, in this video we're going to look at chapter 14 and 15. Our notes are on probability. Alright, so experimental probability is the actual probability of an outcome in the experiment. So what actually happened, what did happen. If I toss a coin 30 times and get 12 heads, what is the experimental probability of getting heads? Well, in the experiment I got 12 out of 30 heads, so 12 out of 30. Or 40%. Theoretical probability is the expected probability of an outcome. So what should happen? Example, using the same coin tossing situation, what's the theoretical probability of getting heads? Well, in theory, we should get 50%, since there are two options, 1 out of 2. Alright, the law of large numbers. As the number of trials increases, the experimental probability should get closer to the theoretical probability. Alright, so I did a simulation flipping coins through like a virtual coin flipper. So if I ran the trial 10 times, so I flipped the coin 10 times, I got 7 out of 10 heads. When I did it 100 times, I got 44 out of 100 heads. When I did it 500 times, I got 233 out of 500 heads. And when I did it 1,000 times, I got 492 out of 1,000. So you can see the percent goes from 70% to 44% to 47% to 49.2%. So it's getting closer to 50%. Okay, so as we increase the number of trials, the experimental probability should get closer to the theoretical probability. All right. Sample space is the list of all possible outcomes. So, for example, what is the sample space when rolling 2 dice? Alright, so this depends on what you're measuring. It could be the numbers 2 through 12, because if you're rolling 2 dice, the smallest you could get is 2 ones, which would have a sum of 2, and the largest you could get is 2 sixes, which would have a sum of 12. Or all the different combinations per roll, so you could roll a 1 with a 1, a 1 with a 2, a 1 with a 3, and so on. Okay, so you could have all those combinations. Alright, so here's some different lingo of probability. So A, B, C, those capital letters are your events. P of A means it's the probability of event A happening. S represents your sample space. And then A, and then the superscript C is the complement of event A. So event A not happening. So it would be event A not happening. If it has that little c, that's the complement. So it's always the opposite of whatever. The 3 probability rules. So the probability of your event needs to be between 0 and 1 inclusively. So all probabilities must be between 0 and 100%. The probability of your sample space has to equal 1 whole, or 100%. The probability of all the outcomes must total 100%. And the probability of your complement is equal to 1 minus the probability of the actual event. So the probability of an event not happening is 1 minus the probability of it happening. Alright, your turn. So on these your turn ones, I want you to try to pause them and see if you can figure them out. And then I'm going to quickly go through the answer. So if the probability of hitting a home run is 30%, what's the probability of not hitting a home run? Alright, so the probability of a home run is 30%. Probability of not hitting a home run would be the complement. So 1 minus 30% leaves me with 70%. Alright, this one. If there are only 8 different blood types, fill in the chart below. Well, I know that the probability has to total to equal 1 whole, or 100%. So if I take all of the probabilities that I know for all the blood types that they were given, and I add them all up, I get 0.94. If I do 1 minus that, I'm left with 6%, or 0.06. So AB positive must be 0.06. Alright, this one. Gambler Jack, when asked to predict the ACC basketball champions, follows the modern practice of giving probabilistic predictions. He says, UNC's probability of winning is twice Duke's. NC State and UVA each have probability of 0.1 of winning, but Duke's probability is 3 times that. Nobody else has a chance. Has Jack given a legitimate assignment of probabilities to all teams in the conference? Why or why not? Okay, so we have the probability of UNC, Duke, NC State, and UVA. Well, they told me that NC State and UVA have a probability of 0.1 or 10%. So 0.1 and 0.1 for NC State and UVA. They also said Duke's probability is 3 times that. So 3 times 0.1 is 0.3 for Duke. And it says UNC's probability of winning is twice Duke's. Well, Duke's is 0.3, so 2 times 0.3 is 0.6. Now, is that legitimate? So if I take 0.6, 0.3, 0.1, and 0.1 and I add them, I get 1.1. So this is not good because it has to have a total of 100, not 110. All right, unions and intersection. A union, the meaning of a union is to representing the outcomes in event A or event B, or both. All right, the symbol looks kind of like a U. And then the example of how it will be written is the probability of A or B. So the union sign, you would say that or B, A or B. The intersection, representing the outcomes that are in both events, A and B. The symbol is an upside down U, okay, kind of like an N. And an example would be the probability of A intersection B, so probability of A and B. So that's more like where they overlap. Alright, so Venn diagrams. Use the shapes to represent events, and then the box around the shapes to represent the sample space, all possible outcomes. Alright, so we have 2 circles, A and B. The probability of A is 0.26. The probability of B is 0.41. And the probability of A and B, where they intersect, is 0.10. Draw the Venn diagram. Well, I know where they intersect, it's 0.10. And I know that A, altogether, that circle for A has to be 0.26. But 0.10 is already used, so that leaves me with 0.16 left. And I know for B, that whole circle has to be 0.41 altogether. And 0.1 is already used, so that leaves me with 0.31. And then if I take all of those, 0.16, 0.10, 0.31, add them and subtract it from one whole, I'm left with 43% that's not in A or B, so it goes outside of the circles. Alright, this example, the probability of A is 0.32, the probability of B is 0.61, and the intersection is 0.22. So 0.22 goes here in the middle. 0.32 minus 0.22 leaves me with 0.10. 0.61 minus 0.22 leaves me with 0.39. And if I add those all up and subtract them from one whole, I get 0.29 that's not in either group. Now I need to find the probability of A or B. So it can be anything that's in A or anything that's in B. So I would add those all up, and I would get 0.71. The next one, it's the probability of anything that's not in A, so the complement of A. That means anything that's not in A. Or anything that is in B. So I can also include everything in B. So anywhere that I've highlighted can be included. So 0.22 plus 0.39 plus 0.29 gives me 0.90. Oops, I went a little far. Alright, and then the next one, the probability of the complement of A or the complement of B. So it's everything that's not in A, so it can't be in A, and it can't be anything in B, so anything that's not in B. So if it's not any bit of A, not any bit of B, okay, the complement is 0.10, 0.39, and 0.29 altogether. Anywhere that was highlighted with the or, the unions, is what I'm looking for. Okay, so 0.78. The next ones, these ones are intersections. So the probability of the complement of A. So anything that's not A is the A's complement. And, so I'm going to change my color here, my highlighter. And anything that's in B. So there's B. So anywhere where those two colors overlap, where it's a little bit of yellow, a little bit of blue, that's where my answer would come in. So 0.39. The next one is the probability of the complement of A and the probability of the complement of B. Alright, so if it's anything that can't be an A, so anything that's not A, and then anything that's not B, leaves me with that. So it's everything. The only section where it overlaps is the outside section. So where there's yellow and orange. Alright, this one, your turn. Go ahead and pause and try this one. Real estate ads suggest that 23% of homes for sale have fireplaces, 65% have a second bedroom or bathroom, and 13% have both features. What is the probability that a home for sale has a second bathroom and a fireplace, neither a second bathroom nor a fireplace, or a second bathroom but no fireplace? So I'm going to fill in this Venn diagram. I know that if they have both features, it's 13%. So 0.13 is going to go in there. For a fireplace, it's 23%. So if I do 23 minus the 13%, that leaves me with 10% of just a fireplace. 65 have a second bathroom. So 65% minus 13% leaves me with 52%. And then if I take the 0.1, 0.13, and 0.52 and subtract it from one whole, I'm left with 25% outside of those. It doesn't have either a fireplace or the second bathroom. So a second bathroom and a fireplace. So that'd be the probability of the bathroom and the fireplace. That's an intersection. And that would be where they overlap right there in the middle is 0.13 or 13%. So they have neither a second bathroom nor a fireplace. That'd be the probability of the complement of the bathroom and intersection, the complement of the fireplace, which would be the 0.25. They have a second bathroom but no fireplace. So the probability of a bathroom and no fireplace, the complement of a fireplace, would leave me with 0.52. Alright, the Venn diagrams can really help when finding these percents or decimals. Alright, so the rule for unions. The probability of A or B, as it's stated on your AP reference sheet, is the probability of A plus the probability of B minus the probability of A and B. So I'm subtracting the part where they overlap. Okay, it's going to get counted. If I count A and I count B, it's going to count that middle section twice. So I want to subtract it one time. So that way I don't have it in there being counted twice. Alright, for a deck of cards, when picking one card, what is the probability of picking a red card or a face card? So it's kind of going to be a little bit important that you know some things about a standard deck of cards. So there's two colors, black and red. There's face cards, king, queen, jack. Starts at ace and goes through 10. We have hearts and diamonds are red. Clubs and spades are black. Alright? And there are 52 total cards in a deck. Alright, so the probability of it's red or a face card. Well, if it's red, I have 26 out of 52. Half of them are red. Plus, I have, for a face card, I have 12 face cards out of 52. But I have to subtract the 6 face cards that are red. and that gives me a probability of 32 out of 52. Okay, and when they ask for probability, unless they state specifically, fraction, decimal, or percent will be fine. Alright, special cases. What if A and B don't overlap? So the probability of A and B equals 0. Picking a red card and a spade. Okay, well, you can't pick a red card that's a spade because spades are black. So this is called disjoint or mutually exclusive. Two events are disjoint if they have no outcomes in common. Alright, the probability of A or B is the probability of A or B. I don't have to subtract out the intersection because it equals nothing. Alright, when picking one card out of a standard 52 card deck, what's the probability of picking a heart or a spade? Well, probability of a heart or a spade. Well, hearts, I have 13 hearts. And spades, I have 13 spades. And there aren't any hearts that are also spades, so I don't have to subtract anything. I get 26 out of 52. The probability of getting a 3 or a spade. The probability of 3, well, I have 4 threes out of 52 cards, and I have 13 spades out of 52 cards. So that would be 1. Oh, I have to subtract out the 1 3 that's also a spade. So that leaves me with 16 out of 52. What's the probability of a queen or a king? Well, the probability of a queen is 4 out of 52. And the probability of a king is 4 out of 52. I don't have any queens that could also be kings, so I don't need to subtract anything. And I get 8/52. A red card or a heart. Well, I have 26 red cards, and I have 13 hearts. But I also have some of my hearts, 13, that are red. So I have to subtract those. And that leaves me with 26 out of 52. A black card or a face card. Well, I have 26 black cards. I have 12 face cards. And I have 6 face cards that are black. So that gives me a probability of 32 out of 52. Alright, your turn. Try this one. Pause it. The probability of event G is 0.25. And event K is 0.35. The probability of G and K is 0.1. What's the probability of G or K? Alright, well, probability of G or K equals the probability of G plus the probability of K minus the probability of G and K. So they gave me all these pieces. So probability of G is 0.25, K is 0.34, and the intersection is 0.1. So if I add them and subtract, I get 0.49, or 49%. Alright, probability rules, intersections, and conditionals. Conditional probability, so the probability of A given B, is the probability of event A happening given that event B happened already. Okay, this formula will be on your reference sheet. So the probability of A given B is the probability of A and B divided by the probability of B. Okay, it's always divided by whichever one is given. So given B, the second one is always what's been given. Okay, and that's always your first event. So working backwards, if you wanted to find the probability of A and B, and you knew the conditional probability, then it would be the probability of A given B times the probability of B. Alright, independence. Some examples would be rolling a die, flipping a coin, picking things with replacement, so you're going to put them back in. If the probability of A given B equals the probability of A, then A and B are independent. So, independent events. We can also check it by if the probability of A and B equals the probability of A times the probability of B. So, I have two different methods for checking independence. Alright, example, probability of J equals 0.23. The probability of B equals 0.67. And the probability of J given B equals 0.15. What's the probability of J and B? Alright, well, the probability of J given B equals the probability of J and B divided by the probability of B. I know the probability of J given B is 0.15. I do not know the probability of J and B, but I know the probability of B is 0.67. So if I multiply both sides by 0.67 and I solve, I get the probability of J and B equals 0.1005, or 10%. Are J and B independent? Well, I have two different ways I could check for independence. I can see if the probability of J and B, which I just found is 0.1005, is equal to the probability of J times the probability of B, which it is not, so no, they're not independent. Or I could also have checked the probability of J given B, is that equal to the probability of J? Well, the probability of J given B is 0.15, and the probability of J is 0.23, so no. Alright, are J and B disjoint? Well, does the probability of J and B equal 0? Well, I just found the probability of J and B, and it was 0.1005, and that is not 0, so the answer is no. And now, with testing for independence and disjoint, if the number is very, very close, then you're probably okay to say that they are independent or they're disjoint, because it's probably just a fractional or decimal small change. Okay, somebody might have rounded and you didn't round the same way. Alright, your turn. Try these ones. The probability of A is 0.45. The probability of C is 0.39. The probability of A and C is 0.22. What's the probability of A given C? Alright, well, the probability of A is 0.22. Or, I'm sorry, the probability of A and C is 0.22, divided by the probability of C, which is 0.39, gives me 0.5641. The probability of C given A, well, the probability of C and A is 0.22, divided by the probability of A, 0.45, which gives me 0.4889. Are C and A independent? No. The probability of A given C does not equal the probability of A. So 0.5641 does not equal 0.45. Are they disjoint? No. The probability of A and C is not 0. Okay, so disjoint, remember, is there's nothing overlapping. Alright, another example. Use the following table about grade level and favorite type of pet to answer the probability questions. If someone is a sophomore, what's the probability they like dogs the most? Alright, so if I'm looking at sophomores, and I'm looking at that they like dogs, I have the probability that they like dogs given they're a sophomore. Well, I have 18 sophomores that like dogs out of 43 total sophomores. Given that someone likes cats the most, what's the probability that they are a junior? So it's given they like cats. So junior given cats. If the juniors that like cats is 13 out of the 47 total people that like cats. So 13 out of 47, or 0.2766. Alright, the next one. We pick a freshman at random. What's the probability they like other animals the most? Alright, so it's other, given I'm picking from freshmen. So 12 like other out of 34 total freshmen, which is 0.3529. Alright, another example. In a bag of gummy bears, 12 were red, 8 were green, 9 were orange, and 10 were yellow. Find the probability that you eat a red bear, then a green bear. So the order in which you eat them makes a difference. So I'm eating a red first and a green second. So the probability of eating a red, well, 12 are red, and if I add 12, 8, 9, and 10, I get a total of 39. So I have 39 gummy bears total, 12 of them are red. And I'm going to multiply that. So when it's the intersection, we're usually multiplying. When it's a union, we're usually adding. Okay? So I'm going to multiply that by, now the number of green that I have is 8. But now that I've eaten a red one, I don't have 39 gummy bears anymore. I have 38. So it's 12 out of 39 times 8 out of 38. The next one. The probability that I eat a red bear and a green bear. Okay, so the order doesn't matter. I eat a red and a green. Maybe I eat a green, then a red. So I have to account for both possibilities. So I have 12 out of 39 times 8 out of 38. That's if I had red, then green. Or I could have 8 out of 39, green first, then red. Okay, and then multiply those all across. If I eat 3 orange bears, well, I have 9 oranges to start with. So I have 9 out of 39 times my next bear, 8 out of 38. And then my next one, 7 out of 37. Alright, your turn. Suppose 40% of cars in your area are manufactured in the U.S., 30% in Japan, 10% in Germany, and 20% in other countries. If cars are selected at random, find the probability that a car is not U.S. made. Alright, so you should be able to do these. The probability that they're not U.S. made is the complement of U.S., which is 60%. Alright, it's made in Japan or Germany, so the probability of Japan or Germany would be 0.3 plus 0.1. There's no overlap, so 0.40. They're disjoint. That you see 2 in a row from Japan. Alright, well, Japan is 30%. Multiply it by itself 2 times. I get 9%. None of the 3 cars came from Germany. So the complement of Germany 3 times. And then with the intersection, you're multiplying those probabilities. So the complement of Germany would be 90%. So 0.9 times 0.9 times 0.9, which gives me 0.729. At least one of the 3 cars is U.S. made. So I have the probability 1 minus, I'm going to take the probability of 1, and I'm going to subtract the probability that none of them came from the U.S. So if I take one whole and I subtract that none of them came from the U.S., that would tell me what's the probability of at least one. Maybe 1, maybe 2, maybe all 3. Okay, so that's 1 minus 0.6 times 0.6 times 0.6, which gives me 0.784. The probability that the first Japanese car is the 4th one you choose. Okay, so it's not Japanese, not Japanese, not Japanese, and then Japanese. So I would multiply 0.7 times 0.7 times 0.7 times 0.3, which gives me 0.1029. Alright, another example. At a local track meet, 62% of the participants were girls. 29% of the participants were from private school, and 18% of the participants were girls from private school. So I have probability of girls is 0.62, probability of private school is 0.29, probability of girls intersecting with private school is 0.18. What is the probability that a randomly selected student was a girl or from private school? Alright, so 0.62 plus 0.29 minus the section where they overlap gives me 0.73. What's the probability that a randomly selected girl was from private school? So, given I'm selecting a girl, what's the probability they came from private school? So it's private school given it's a girl. Well, the intersection is 0.18 divided by the probability of girls, 0.62, gives me 0.2903. What's the probability that a randomly selected public school student was a girl? Alright, so public school means it's not private school. So the probability that it's a girl, given they're not coming from private school. So the intersection is 0.44. And then it's out of 0.71. Okay, so it's those complements. So we get 0.6197. Alright, Is being a girl and being from private school mutually exclusive? Does the intersection equal 0? No, so they're not mutually exclusive. Is being a girl and being from private school independent? All right, so yes. If I look at the probability that they're from private school, given they're a girl, is that equal to the probability that they're from private school? Well, private school, given they're a girl, was 0.2903. Oops. And the probability that they are from private school was 0.29. So those are very, very close, so we would say yes. Alright, the next thing, tree diagrams. Alright. An airline offers discounted tickets to customers who buy tickets early, more than 30 days. The company has noticed that 60% of the customers take advantage of the early bird fares, while 25% purchase regular fares and 15% are last-minute customers, less than 48 hours. They have also figured out that the no-show rate among early birds purchasers is 30%, and only 8% among regular fare customers, and 2% among last-minute customers. Create a tree diagram for this situation. Okay, so I have 3 things to start: early, regular, or late ticket purchasers. Well, I know that 60% purchase them early, 25% at the regular time, and 15% late or last minute. Then I'm looking at if they make their flight, if they're a no-show, or they show up. So I have those branched off. For the early flights, it told me that 30%? No, yeah, 30% are no-shows. So that means 70% show. For the regular flights, it's 8% are no-shows, which means 92% show. And for the late, 2% are no-shows, which means 98% show. And then what I'm going to do is I'm going to multiply across. So 0.6 times 0.3 gives me 0.18 for the probability that they were early and a no-show. 0.6 times 0.7 gives me 0.42, the probability they were early and they showed, or they booked early and they showed. 0.25 times 0.08 is 0.02, and so on. So I'm multiplying across, and I'm just writing the label as to what that probability represents. Alright, what's the probability of being a no-show overall? Alright, so the probability of a no-show overall is I took all the no-show pieces, so 0.18, 0.02, 0.003, and added them up. What's the probability of being a no-show and a last-minute customer? Alright, so no-show and a last-minute was 0.003. Given that you have a no-show and a certain seat, what's the probability of that person being a last-minute customer? Well, the probability that they were last-minute, given they were a no-show, the probability that they were last-minute and a no-show, divided the probability of a no-show, and I get 0.0148. Given that you have a no-show in a certain seat, what's the probability of that person being a regular fare customer? Alright, so the probability they were a regular fare, given they didn't show, is the probability of the intersection divided by the probability of a no-show. So 0.02 divided by 0.203 gives me 0.0985. Alright, given that you have a person show up for a certain seat, what's the probability that person's an early bird customer? Alright, so the probability that they were early, given that they showed up. Well, the probability that they were early and they showed up divided by the probability that they showed up. So to get the probability they showed up, I have to add up all the showed up on time probabilities. And I get 0.527. Alright, another example. There are 2 textbook making companies, A and B. It is known that 1% of Company A's books are defective. It is known that 2% of Company B's books are defective. Sun Lake High School gets 38% of its books from Company A, and the rest from Company B. Make a tree diagram below, then answer the questions. Alright, so I have company A and company B. And then I have defective or not defective. Alright, so company A, 38% come from company A, 62% come from company B. Company A's defective rate is 1%, so 99% are not defective. 2% for company B, and 98% not defective. When I multiply across, here's what I get. If I label them, that's what I get. Alright, what's the probability that a book is not defective? Alright, well, the probability that it's not defective, if I add those all up, the 0.3762 and the 0.6076, I get 0.9838. If a book is not defective, what's the probability that it came from company B? So, it came from company B given it's not defective. Alright, so I'm looking for the intersection of B and the complement of defective, which is 0.6076 divided by the probability that it's not defective, which we just found. I get 0.6176, so 62% about. If we open a book and it is defective, what's the probability that it came from company A? And then what's the probability it came from company B? Alright, so the probability it came from A, given it's defective, is the intersection of A and defective divided by the probability of it being defective. Same with B. So it's the probability of B and defective divided by the probability that it's defective. And we get 0.7654. Alright, your turn, number 8. I want you to pause and try this one. A VCR manufacturer receives 70% of its parts from factory A and the rest from factory B. Suppose 3% of the output from A are defective and only 2% of the output from B are defective. So I have company A and B. I have defective and non-defective. There's all my percentages. If I multiply across, oops, that's what I get. Okay, what's the probability that a received part is defective? So it was 0.027. If a randomly chosen part is defective, what's the probability it came from factory A and then factory B? Probability it came from factory A, given it's defective, was 0.7778. Probability it came from factory B, given it's defective, is 0.2222. Alright, this one. Try this one. A particular football team is known to run 30% of its plays to the left and 70% to the right. A linebacker on the opposing team notes that the right guard shifts his stance more of the time, 80%, when plays go to the right, and that he uses a balanced stance the rest of the time. When plays go left, the guard takes a balanced stance 90% of the time, and the shift stance the remaining 10%. What is the probability that a play will go to the left if the guard is balanced? So I'm going to make a diagram. I could go left or right, and I could have a shifted stance or a balanced stance. Alright, so 30% of the plays go left, 70% of the plays go right. If I'm going left, 10% of the time I'm shifted, 90% of the time I'm balanced. If I go right, 80% of the time I'm shifted, 20% of the time I'm balanced. So there's my tree diagram. And asks, what is the probability that a play will go to the left if the guard is balanced? So the probability it's left given their balance is the probability of their left and balanced, which is 0.27, divided by the probability of it just being balanced, which is 0.27 plus 0.14, which is 0.41. And that gives me 0.6585, so 65.9%.